Okay, another aspect of how to think about the instructional design side of this. How many of you know Bloom's taxonomy? Raise your hand. Most people know Bloom's, right? So developed decades ago by a committee before there was a lot of learning science. Good logical decomposition, helpful, but not well tied into how learning actually seems to work. So a group at Carnegie Mellon and the University of Pittsburgh, there's this Pittsburgh Science of Learning Center out there, they decided to create a new framework, a different taxonomy of learning outcomes that does link to what the research says about how learning works. And this is what our instructional designers actually use every day when they're working on their best form, of course. So the first thing is a cognitively complex procedure. So procedure here is not meant to mean trivial. This could be like write a 3-page summary of a 10-page paper. Okay, that's a thing many people will have to do over and over again, is write a synthesis or a summary and so forth. So you can get good at this, but boy, that's not, that's a real task. It's a chunky, important task to do. Now, that kind of thing is supported by other kinds of outcomes that are knowledge components. So facts, you gotta have some facts to do certain things. And so, the kind of practice that really helps with this is not just memorize facts on white pieces of paper, it's actually have practice exercises where you are recalling these facts in a work or a task context. So you have some distractions, you have some environment, because the environment is part of the context that will let you pull it up later. I mean, if we were computers, this wouldn't matter. But we are not computers, and so getting a full context around a thing you're trying to be fluent and fast with is actually helpful to us. So part of it is doing it in a real-world task context. Second thing is concepts. These are different than facts. So a concept is used by experts to classify a situation. Is this an energy problem or a momentum problem in mechanics is actually the critical thing that good mechanics problem solvers do right at the beginning of one of these problems. Novices tend to think, oh, it's an inclined plane problem, or it's a spring problem. That's the wrong way to classify them. It doesn't help you get a solution. But energy or momentum gives frameworks that make a lot of these problems come clean. So it's not enough to define the concepts and know what an energy problem looks like. You have to actually be able to classify. So the right practice for this is to become good at classifying. Now the nice thing about this is classifying is much faster than solving. So you can practice the classification challenge much more quickly than just solving every one of those things all the time. You can make a concept down payment by working on classifications separately, and examples and non-examples. Then there's processes, so you could have things like a Krebs cycle or an internal combustion engine, many sequence steps with different inputs. And again, it's not enough to memorize the steps. The way experts use processes, there's 2 directions they use them. One is changing inputs at any stage. They know very accurately what's going to happen to the output. Because sometimes you change the input and nothing happens. Sometimes you change the input and, tons actually, breaks down. The other way they use them is diagnostically. I have a bad output. The car is pulling into the mechanic shop, there's smoke, there's noise. The guy's already reaching for the right wrenches because he knows what the problem is. So he's able to go backwards very quickly through the process and say, it's got to be here, somewhere in here, so I know what I'm going to look at. And you can actually automate some of that kind of diagnostic stuff. The final area that's critical, experts are really good at handling foggy, difficult areas. Things that are mysterious, you don't have enough information to solve them. Experts are actually great at saying, well, all right, I don't know what else to do, but we're going to start like this. And it's principles. They use principles to help navigate the fog. And again, it's not enough to know the principles. The 5 principles of being a historian. That's not it. You've got to be able to apply them, and that's the practice. Try it in several foggy circumstances. And, concepts, processes, principles, by the way, this is where conversations with experts comes in. It's going to be hard to automate a lot of the gray area conversations. You really need to link up experts to give feedback and help people understand, well, how did you do this? Sometimes there's more than one way to do it, and it may not be enough to have peers talk to each other either, because sometimes peers will convince each other of the wrong thing. So this is where hybrid learning environments become essential, of getting experts to connect on the things that matter the most in terms of decision making and so forth, especially when it's foggy. Okay, Final brief thing on this, the kind of the cognitive underpinnings here, motivation. So we want people who can practice well, get test stuff done, be fluent, be good at work. Now, this is actually hard work to actually get good at this stuff. So we need people to be motivated. And within a lot of cognitive psychology work, the definition of motivation that's important here is, will students or learners start, persist, and put in mental effort? You'll notice the word liking is not on that list. Okay, this is really important, right? Because often smile sheets, right? Now, liking can drive these three things, but it's just like, weightlifting or doing wind sprints for an athlete. You can hate every second of working at the bar as a dancer. And if you do it reliably and well, your body will get stronger. It will be more flexible while you hate it. Okay? And when you ask those people why are they doing it, it's not because they hate it, obviously. It's because they need it. They are motivated to sprint, to push weights, to do scales or whatever it is because of the outcomes. That's motivation. And learning and brains and all that, if you start, persist, and put in mental effort into well-designed learning activities, you're running your neurons properly, you will change them. So that's why this is really the correct definition of motivation, not the liking thing. So we had a very good cognitive scientist, Richard Clark, do a scan of a lot of different areas of motivation research to see if he could pick up some themes that were common. And he came back remarkably and said, it looks like in different language and different domains, there appear to be 4 major things that go wrong with motivation, defined as starting, persisting, putting in mental effort. The first one is learners don't value what they're doing. Dancer in an algebra class, what am I doing here, right? I want to go dance, so I don't start, persist, put in mental effort. I'm thinking about Swan Lake, right? So you have to talk to that dancer, motivate them in some way about why this could matter to their future, their careers, running a dance company, a foundation, etc. Second problem, very different than the first one. Another dancer in the same algebra class, but that dancer is thinking, I can't do math. I can't do math. Now, if the faculty member approaches that student and says, it's so important for your future as a dancer, let me show you examples, and that dancer is sitting there thinking, I know, my life is over. This is a disaster. I can't do it. I hate my life, right? You're not helping, right? That's not the intervention. The correct intervention is to not agree, to say, of course you can do math. We just have to back it up enough. Let's look backwards and see where we're missing some things. There's probably stuff not in long-term memory that needs to be in there. Let's figure it out. It turns out there's a bunch of research that shows cockroaches, cats, bears, and dogs can do simple math up to the number 2. So come on. We can do math. No, don't invite me to talk to your students. I know. Yeah, right. So then there is this whole range of research about specific instructional design techniques coming from people like Richard Mayer and others. Who here knows who Richard Mayer is? Yeah, this is a room that knows who Richard Mayer is. Yeah, and he's done this work for decades, and it's almost never applied at scale by any of your colleagues up in San Francisco in the education technology sector. They have never heard of Richard Mayer, right? It's extraordinary. And we won't go through all this. There's a bunch of great things he's done. This book, E-Learning in the Science of Instruction, is a fabulous handbook of applying learning science by instructional designers. It's very practical. If anybody ever asks you, what should I look at? This is a great volume because it's intended for instructional designers, grounded in evidence. And this stuff is subtle. So it's things like multimedia, good or bad for learning? Has anyone ever seen the study, pencils, good or bad for learning? It's meaningless, it's the wrong question. So if you have audio and visuals tied together about a hard concept, you're working both channels into working memory, you actually get real benefits from that, more than a standard deviation of benefit. However, if your audio is a distraction from the actual hard concept you got there, you get exactly the opposite, more than a standard deviation of detriment. So it's not multimedia, yes or no. It's what is the use of media that can drive learning versus distract from it, right? And there's a whole range of these kinds of outcomes and research results where, imagine, and the business guys can be bad about this. It's like, come on, Bror, boil it down. I just need like the 3 bullet points on learning. And so I turn around and say, you know what? If you can give me the 3 bullet points on cancer treatment, I'll give you the 3 bullet points on learning. Because cancer is complicated. Right? You agree with that? Oh, yeah, it's really complicated. What do you think, a brain? How about that? How does that sound? That's complicated too. So we have to kind of accept the evidence-based complication of this kind of work. So you guys don't need this primer, but if you can move a 50th percentile player by a full standard deviation, you get him to the 84th percentile. So those results on the previous page, lots of one standard deviation things, this is major stuff, but those are laboratory results, right? So engineering work, it varies in the real world. So how about the real world? So a couple of things here. This is an example of a bit of a dirty laundry. We did a scan of 9 different products at Kaplan across a wide array of pieces with a cognitive science-infused checklist that we actually built with the Gates Foundation about 4 or 5 years ago. The dark is good and the light is poor, and it's not all that pretty a picture. Even some things that we ought to be very good at, like writing objectives, that's not that hard. We had several examples where there were no objectives. It wasn't clear what the point was. Right? Which is like, ask a university teacher, what does he do? He says, I lecture. I talk about what I talk about. I was like, oops, right? There's other things like personalization that can be very expensive to do, and so probably don't need to be top of the list of things to do, but you've got to fix the assessments. We've got to fix the outcomes. And this is hard even for us to do, so we're working on these things. Our intuitions can be bad for this. Here's an example looking at teacher-graded essays. So on the left, yeah, it shows up. On the left are the teacher's marks given to an essay out of a composition course. And on the right are when we gave it to 2 different teachers, not who had the students, but used the same rubric. Houston, we have a problem, right? Now, interesting, you don't actually know what the problem is. Everyone would assume, oh, those teachers are putting the thumb on the scale, are being helpful to students. Could be the rubric is so bad that, in fact, the only way you can give the right mark to a student is by knowing the student's work. And therefore, the other 2 teachers, they had no idea, so they got no hope of getting the right mark. All we know is this is not a valid and reliable assessment method. So we're trying to fix it by figuring out better training, trade papers. We're going to fix this. But you can't use this to do randomized controlled trials. It's terrible, right? It's not what we need. And this is how it's been done for hundreds of years. Right? This is the intuition of how we should do it. It's not going to be very effective, especially for performance things, right? Grading an essay piece with a rubric is a performance thing. Here's another example of a piece where we're very good at training students, training people to pass the LSAT, the law school admissions test. We've been doing it for decades. And we know the hardest part of that is the complex reasoning problems, really challenging. So we created a video, the Kaplan way to solve complex reasoning problems with a workbook, an hour and a half of beautiful media production. And then one of our learning engineers said, I'm betting that's not actually the best way to do it. Why don't we try worked examples? Anybody here know John Sweller's work, worked examples? If you've been going on for decades, things that are really cognitively complex that overload students' working memory, show worked out examples by experts before you give them the problems themselves. We ran a randomized controlled trial, and on the right, those are students who got nothing. The next column on the right after that is, yes, it is Kaplan's hour-long video plus workbook. So the first thing is, Kaplan, worse than nothing. My marketing colleagues say we can't go out with that. Okay, now the good news is statistically, the 2 right-hand bars are the same. So it's like, whew, Kaplan, as good as nothing. No? Not inspired? No? All right, not helpful. Now, look, it isn't because people knew this was not going to work. Everyone assumed that if we did a serious video, our best people talking about it, yada, yada, this would help students. What this demonstrated is no. And in fact, the 2 on the left, one of them is 15 worked examples, one of them is 8. They're statistically the same. And so these are better. These are statistically better work. But here's the real kicker. Look at the amount of time it took. It took 8 minutes to do 8 worked examples. It took more than an hour and a half to do the Kaplan video and workbook. So 8 minutes of a cognitive science-infused approach, better performance, less time. And it was 8 PowerPoint slides, people. Think of the cost of production compared to a lovingly crafted hour-long video and a workbook, right? And actually, it created consternation in the product development group at Kaplan Test Prep because video is so cool. We got to do video. What are we going to do? What are we going to do? And the answer is you should do what actually works for students when it's really hard for students, right? And so they backed fully away from this whole video approach. But this stuff is hard to do. We actually, through the Cognitive Science Kitchen Sink, had a bunch of online courses. We did motivation work. We did redoing the screens. We modified the structure to make sure one objective was taught in one lesson. And if we needed two objectives to happen, we combined them. We did everything, which is not what a scientist would do. Right? This isn't science. This was engineering to see, what if we throw the Cognitive Science Kitchen Sink at it? And what we were able to demonstrate is students with almost 1,000 students across 3 different courses, control and pilot, students were 1.5 times more likely to be successful, where success was defined as they passed the course, so GPA, they mastered critical outcomes, we had those for every course ahead of time, and they came back. You can't learn if you're not here. They had to come back, right? And this led Kaplan University to start a whole series of randomized controlled trials trying to do smaller pieces because they were wondering, well, so Bror, which of these things worked? And it's like, guys, we just threw the kitchen sink at it. Now we have to do some work to figure out, are there inexpensive things that work better and so forth and so on. So that's all about that. Another quick example, dashboards for faculty. Everyone would think, give data to faculty. This will be great. This will be great. That's what we should do. And it's actually tricky. So we tried 3 different ways of giving data to faculty. One way, we gave them some attendance data to online seminars that they could follow up on if people didn't show up. What we found is we improved retention, but we didn't improve academic performance. So the second thing we did was we looked to see submissions. Did you submit your assignments on time? And here what we found is we actually got both things to improve. We actually got both to improve, both the retention and learning outcomes. So that's a win. The third thing we tried was measures of how long people were working in the platform and then gave dashboards based on that. And there, didn't change the retention at all, but actually helped the academics. So, the picture's not simple. Why didn't it move all of them? Unclear. So now we're doing pilots, more complex combinations of these to see what would happen. This is engineering, right? We rolled out one of these because it seems to affect both, but now we're continuing to explore this. So, because of all the kind of scale that we have, we're able to do many different randomized controlled trials. So we're running now a whole program of work against many different themes. We're actually working over at Stanford with some folks on motivation work, the PERT Center there, which builds on some of Carol Dweck's work on motivation. And it's really frustrating because it doesn't work at all the way it works in the higher ed brick and mortar institution. And those guys are banging their head against the counter saying, why doesn't it work? Why doesn't it work? It's worked before. Why doesn't it work? It's like, yeah, this is engineering, right? This is what you have to figure out. You can't give up because it's very promising. So something isn't right, and we've got to figure out what that is, and that's just how you do it. So the final piece is, to get people ready to do this kind of work, it's real work to train people. This is, non-trivial things. So we have a training program that starts with an online self-study piece that's part-time, 40 hours of work, and then there's a workshop where people get together to get ready to work on a project together, coached by an expert who's done this before, so that they can see each stage of it and get coaching on it themselves. Yes, these are our instructional designers and our lead instructional designers. Because, note to everyone, instructional designers have human brains too. I know that's a shock. We could do a research study together. I don't have a randomized controlled trial to prove it, but I believe that's the case. And that means everything that we've talked about applies to your professionals as well. The motivation thing applies to faculty. How come these faculty aren't doing it? Well, figure it out. Do they not value it? Do they think they can't do it? Do they blame other things in their environment, et cetera, right? So, we can apply all these ideas to our own staff, and that's how we built this, to try to apply the same ideas of practice and feedback to our own staff. And that's the only way you can get, this kind of thing to work at scale, is to invest in these kinds of systematic processes if you're going to try to get good learning engineering done. So thank you very much for your time and attention.